Welcome to Biology Made Easy. In this lesson, we have review questions and solutions on topics already done on water potential, solute potential, pressure potential, tension. Welcome. The first 5 questions will be on cells, turgid, flaccid, plasmolyzed. And so please fill in, take a pen and paper and look at the first 5 questions. Well, water potential is affected by solute potential, pressure potential in a relationship like this. This is the relationship. Well, fill in blank spaces with the following terms: water potential, solute potential, pressure potential, less negative or more negative. As water moves from hypotonic solution into a cell, 1, dash potential of the cell increases, dash negative. Dash potential of the solution increases, dash negative. When a cell is fully turgid, dash is maximum. When a cell is losing water by osmosis, the structure that loses water first is dash, and the structure which loses most water is dash. At incipient plasmolysis, dash potential is 0. A plasmolyzed cell can regain full turgidity when placed in isotonic solution, hypotonic solution, hypertonic solution, pure water. We'll have a very quick review on cells. First, this is a turgid cell. This cell has taken in a lot of water from the surrounding solution, and the cell is turgid. If it's turgid, it means the contents of the cell presses on the wall. That is pressure potential. Well, when a cell is flaccid, it has incipient plasmolysis. It's the point where plasmolysis is just beginning to occur. It means that this flaccid cell has lost so much water because it was put in a hypertonic solution. It has lost so much water. What happens to the pressure potential? Is there any pressure potential at this point? Are the contents and the water inside pushing on the outward on the wall? That would be its pressure potential, isn't it? Well, this is also a plasmolyzed cell. When a cell is plasmolyzed, how can it regain full turgidity? What solution can it be placed in? Isotonic, hypotonic, pure water, etc. These are facts you need to know about before you answer the first 5 questions. Besides that, we need to quickly revise also on water potential, which we did. Pure water is at its highest water potential and it's set at 0. So water that is less concentrated, it has plenty of water, less solute, it has high water potential and it's less negative. But water that has a solution that is highly concentrated, the more concentrated a solution becomes, the less water it contains, and the low water potential it has, and the more negative it becomes in Pascal values. Well, we also need to remind ourselves of solute potentials. When there's very little solute in a solution, it means its solute potential is low. Very little solute in a solution, like here, its solute potential is low. And you know, solute potentials are always measured in negatives. So if the solute potential is low, it has low negative. If it has plenty of solute, the solute potential is high, it will have great negative. So let's get to answer our questions. The question 1 says, as water moves from hypotonic solution into a cell, the dash potential of the cell increases, dash negative. Water potential increases, it becomes less negative. And then dash potential of the solution increases and becomes dash negative. And we have solute potential of the solution is what increases. And when solute potential increases, it becomes more negative. Then when a cell is fully turgid, the contents are pressing on the cell wall, its dash pressure potential is maximum. Then we have when a cell is losing water by osmosis, the structure that loses water first is the cytoplasm, because water will have to move from the cytoplasm into the external solution. But the structure that loses water most is the vacuole. And you see, the vacuole loses water and the cell protoplast shrinks. And at incipient, plasmolysis is just about to begin. So at this point here, at incipient plasmolysis, the pressure potential is what is 0. Well, at incipient plasmolysis, as we have said, the pressure potential here is 0, then it means that at incipient plasmolysis, if the pressure potential is 0, this is 0, pressure potential here is 0, then it means that the water potential is the same as the solute potential of the cell. And if you work it out, this is the equation that you get. Because no water is moving in or out of the cell. So the water potential of the cell is the same as the solute potential of the cell. So if you come here, that's it. The water potential of the cell here is the same as the solute potential of the cell. Everything is equal in here. Pressure potential is 0. And the solution that bathes the cell, the water potential of the solution is the same as the solute potential of the solution. Everything is at equilibrium. That is at incipient plasmolysis. This is the equation. Then we have a plasmolyzed cell, question 5. A plasmolyzed cell can regain full turgidity when placed in what? So this cell is plasmolyzed. We have plasmolyzed cell here. If it's placed in a solution that is less concentrated than the contents here, water will move in and water can move back into the plasmolyzed cell. If it's placed into a hypotonic solution, water can move back into the cell. But to gain full turgidity, this is the term, to gain full turgidity will need to be placed in pure water. Good. So let's now look at another question. This one. We have 2 cells, neighboring cells. This is cell A, cell B. These are their values of water potential, pressure potential, solute potential. Which cell, A or B, has high water potential? Right? Less negative. Which of these cells? Okay. Then we have another question. In which direction will water move by osmosis from cell A to B or cell B to A? Looking at the values that has been provided. This question C here. At equilibrium, the 2 cells have the same water potentials, which will be the average of the 2. So cell A has this water potential, cell B has this water potential. If the 2 are put together, we'll have water potential of 2,000 pascals. The average will be 1,000. That's how the water potential of the 2 cells is worked out. And the question is, assuming the solute potential does not change significantly, what will be the pressure potential at equilibrium in cell A and cell B. So let's get to answer the questions. Which cell has a high, less water potential? It's cell A, isn't it? Because look at it. This has a high water potential, right? We have explained water potential enough. So in which direction will water move? By osmosis. Of course, in which direction is the water potential high? Because water moves from a region of high water potential to a region of low water potential. And here is a higher water potential. We've explained that. So it's from cell B to A. Well, then we have at equilibrium, the two cells have the same water potentials. And this is the same water potential, assuming solute potential does not change significantly. What will be the pressure potential in cell A and B? So in cell A, this is the equation to work out the pressure potential. This is the values we have. This is the pressure potential. Pressure potential is always positive. Well, what happens in cell B? This is the pressure potential in cell B. Putting the values in, all right? 1,000 here. Cell B has solute potential of minus 1,400 pascals. So it's put in here. So this is what you have, pressure potential. Now look at it. The pressure potential of cell B is 400 pascals. The pressure potential of cell A is 1,000 pascals. But the two cells are at equilibrium. Water is not moving from anywhere. And their equilibrium, the solute potentials are slightly different. And so is balanced by the slightly different pressure potentials. So the cells at equilibrium. Very neat. Now let's get on to another question. And this time is on water potential gradients and hydrostatic pressure gradients and tension gradients. Well, this is the stem. During transport of water in plants, any of these three listed gradients can be referred to. Can refer to water potential gradient, hydrostatic pressure gradient, tension gradient. Choose suitable combinations from the table below. So we have potential or tension at the top of the tree, potential or tension below the tree. And we have to work out water potential at the top of the tree is low. The water potential below the tree is high. And the question is, if it's high, is it less or more negative? If it's low, is it less or more negative? Then we come to hydrostatic pressure. At the top of the tree, hydrostatic pressure is low. The question is it less positive or more positive? Below the tree, hydrostatic pressure is high. Is it less positive or more positive? Then we come to tension. Tension at the top of the tree is high. Question, is it less negative or more negative? Tension below the tree is low. Question, is it less negative or more negative? Well, to remember what these are quickly, we want to quickly revise what we said about hydrostatic pressure, the pressure of a fluid at any point in equilibrium acted upon by gravity. So the hydrostatic pressure at this point here, at point A here, will be lower than at point B because of the weight of the water is high in point B. So hydrostatic pressure increases as you go down. So if the top of the tree, hydrostatic pressure will be lower here and higher here. Meanwhile, tension is pulling force. So the force to pull water from the surface, and we are pulling the water right from beneath. So tension is highest at the top of the tree, at the top, than below. And tension values are negative. So tension is highly negative at the top. And we brought it to look at it. This is a section we looked at in our lessons. We have a section of the leaf, the stem, the root, and we looked at the figures of water potential. See, the water potential in the top here, very little water. Evaporation is taking place. The salt solutions are concentrated, so water moves in. And so the water potential at the tops here is low, very low, and very, very negative. And as you go down the tree, the water potential becomes high and less negative. Meanwhile, hydrostatic pressure is low at the top, and as you go down, the hydrostatic pressure increases and is positive. Tension is highest at the top of the tree to pull the water up, and tension is lowest. And the higher the tension, the more negative pascals. So let's answer our questions easily here. So these are the answers. At the top of the tree, low water potential means more negative. High water potential means less negative. Low hydrostatic pressure at the top of the tree means less positive. High hydrostatic pressure below the tree means more positive. High tension at the top of the tree means more negative, and low tension below the tree means less negative. Now we'll get to our last question, which is on phloem. Here's the question. If sucrose is actively loaded into the sieve tube, which combination of changes takes place in the sieve tube? Now, as sucrose is loaded into the sieve tube, let's look at the phloem. Here is a companion cell. Here is sieve tube, another sieve tube, sieve plate here, and we have phloem parenchyma cells very close to the sieve tubes, and we have phloem fibers. This is a phloem fiber that is strong, strengthening the phloem area. Now, this sieve tube, sucrose that is made in the leaf is pushed into the sieve tube, active transport, directly into the sieve tube, and also sucrose is put into the companion cells and finally end into the sieve tubes. So sucrose manufactured in the leaves is loaded, filled, pushed into the sieve tubes. And when sucrose is pushed in, what happens to the sucrose potential? It will increase. And when sucrose potential increases, what will it become? More negative. But when sucrose comes into a cell, water in the cell, amount of water will reduce because the water molecules will dissolve the sucrose. So once sucrose moves in, the water potential will decrease. Hydrogen ions will decrease. That is why when sucrose moves into the sieve tube, water will flow from the companion cells into the sieve tubes. And that increases the hydrostatic pressure. Okay, so this is the question. If sucrose is actively loaded into the sieve tube, which combination of changes takes place in the sieve tube? Solute potential decreases. Does it decrease? No. Solute potential will increase. So right away, it's wrong. Here, solute potential will decrease. No, it doesn't. So the whole thing is not true. Solute potential increases, yes, And once solute potential increases, it can become more negative, but we have less negative here. It's better. Here, we have solute potential increases, yes. And in both cases, we have less negative because solute potential values are negative anyway. So less negative, less negative. Okay, so the answer is between these two, all right? But when solute potential increases, the hydrogen ion concentration in the system, will it increase or decrease? Here we have hydrogen ion concentration decreases. Here we have hydrogen ion concentration increases. Which one will you choose? Let's go and choose the right ones. Here, you see? Because these two, solute potential decreases as solute is moved in. It's wrong. It doesn't decrease, it increases. So this is it. Solute potential increases. Well, it becomes less negative. Solute potential is always negative. And hydrogen ion concentration decreases because the water potential will decrease, because the water in there some of it will surround the solute. So the hydrogen ion concentration will decrease. Hydrogen ion concentration will not rather increase. So the answer is C. C is the answer. Well, this brings us to the end of our lesson for today. We hope we have been helpful. Please give us thumb. Please subscribe. And thank you very much. Goodbye.